Hello, my name is Jared Skeens, and welcome to the Zoom room. Today, we'd like to look at Pure Maths 1, Series, Part 1, Binomial Expansion. And as always, I like to work on training the mind before we work on training the skill. We've got a lot to cover, so let's get started here. Here at the top, you're going to see a formula. Now, this formula is in the formula sheet that is provided by Cambridge. Okay, so this is what the formula sheet that's provided by Cambridge looks like. It's called List MF19. This is the new updated version. It's several pages long, and we haven't discussed this yet throughout the Pure 1 series. The only formula that we've actually covered was back in quadratics. You can see here in the middle, you can see the quadratic formula. So the quadratic formula is actually on here. So technically you don't have to memorize it, but you should anyway. Other than that, we haven't covered anything that's in the formula sheet. Like I said, it's several pages long. It covers all of Pure Maths 1, Pure Maths through Pure Maths 3, Statistics 1, Mechanics 1. It actually even covers things from further maths. So the reason why I'm pointing this out to you now is because we're starting to get to some of those formulas that you should be aware of. And here you see binomial series, and there are two formulas plus some notation in here. So this formula right here is the one that we're on. Says n is a positive integer. Down here is a similar formula, but this is when n is not a positive integer. So if you have your formula sheet with you, you might want to look at that while you're looking at the video. And this one down here is actually covered in Pure Maths 3, okay? So this one is the one that we're on right now. And what I want you to particularly notice is this notation right here. I have substituted a different notation in for that. That's what I want to talk about right now. So this is the same formula, but I've made a couple of little changes. The first one, you saw this notation here. I'll talk about that in a little bit later. And I've substituted it with this notation over here. The reason why I've done that is because this notation is what you find on your calculator. So when you're working with your calculator, you're going to see right here under the orange AC key, you see that NCR. See that NCR? And over here you see an NPR. So you're going to want to use that NCR key. It's actually this button under the AC button, and it's the shift this button here to get that NCR. So that is what you're going to use on your calculator, and that's why I use this notation instead of this notation. We'll discuss this a little bit later. So I put this NCR notation, which gives us the coefficients, okay? Another thing that I've done that's not in the formula sheet is I've put in things like these zeros. So if you have n, whatever n number happens to be, and you do NC0, well, it's going to be a 1. And so basically it's not significant to your coefficient. And so the formula in Cambridge doesn't even put it because it just turns into a 1. Same thing with this b to the 0. Anything to the 0 power turns into a 1. So same thing over here. This a to the 0 would be a 1. They don't include it. And this NCN is also a 1. So they don't include that. I have included it so that you can see the pattern. Math, or part of math, is pattern recognition. If you can recognize the pattern, it mentally helps you know what you're looking for as you get into the skill side of things. So I've added those kind of things that normally would cancel out for the purpose of establishing a pattern. Okay, so this is the formula. What we're dealing with is a binomial expansion. Binomial means two terms. Bi means two. Nomial is your term. So you have two terms. So here we have two terms represented by A, the first term, and B, the second term. Now remember, a term includes four things: sign, coefficient, variable, exponent. So the sign can be plus or minus. The coefficient is some number. The variable, generally we're using x or y, and then the exponent of that variable. So A just represents that first term. B represents the second term. And this binomial is going to be raised to a particular power. And so expansion means we're multiplying it out. So we're taking this binomial to a power and we're multiplying it out so that you can see all the terms of the expansion. Okay. So what we want to look at now are the patterns. But before we get to that, we should note, as I was pointing out on the formula sheet, this formula is specifically for when n, that means the power that we're raising our binomial to, is a positive integer. Okay, so integer means there's no fractions or decimals, and it's positive. So you could also call those natural numbers. So the natural numbers are like the positive side of the integer range. Okay, so positive integer. And here, what we want to look at is at least a few examples. So what if our binomial is raised to the 0 power? That's the lowest power that we're going to look at, because although technically 0 is neither positive nor negative, we're going to use 0 as our reference point, okay? So anything to the 0 power just becomes 1. So technically the 0, you're not going to be dealing with a power of 0, okay? You're going to be dealing with a power of positive integer. But we're going to use that as a reference point. Anything to the 0 power is 1. So obviously we're not going back into the negative numbers. Anything to the first power is just itself. So that means you would get 1a plus 1b. You get what's inside. So now as we move forward, things are going to start developing a pattern for us. So as we do a plus b squared, maybe you're used to doing a plus b times a plus b using like the smiley face method or the FOIL method or whatever method you've learned for expanding a binomial. But if you do that, you're going to end up with 1a squared plus 2ab plus 1b squared. Now again, I'm putting the ones. Normally you wouldn't write the ones, they're understood. Again, I'm writing the ones so that you can see a pattern develop. Then we get to a plus b cubed. If you want to do it on a scratch piece of paper and take this, the a plus b squared, and multiply it by another a plus b and see what you get, this is what you would get. You would get 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. And if we went further to the fourth power, this is what we would get. Notice there is one more term in the expansion as what your power is. So here's a 0 power, 1 term. Here's 1 power, 2 terms. 2 power, 3 terms. 3 power, 4 terms. 4 power, 5 terms. Okay? Now, let's start looking for patterns in this expansion. These patterns are going to help us when we get to the skill part. Okay? So there's one pattern that deals with the coefficients, and there's another pattern that deals with the variable exponents. So let's look at the coefficients first. Here I have in blue all the coefficients that have come out of this, these expansions up through the fourth power. And I've taken those same numbers and I put them over here in this triangle form. And this is actually referred to as Pascal's triangle. Now, Pascal lived in Europe, and actually, to be fair and honest in mathematical history, you can actually find this, I think, several centuries earlier in some Chinese writing by a guy named Yang Hui. Hopefully I pronounced his name correctly, but Yang Hui's triangle, I don't know what they called it, but you can find it in Chinese literature several centuries before. But since a lot of our math comes from the European side or the Western side, this is referred to as Pascal's triangle, and this is referred to as Pascal's notation here. So what the Yang Hui and Pascal realized is that when you expanded binomials, there is a pattern to the coefficients. And if you make this triangle, you see we've got 3 1s here at the top. And as you move down, if you add the 2 numbers above it together, you get the next coefficient on the next level. So 1 and 1 make 2. 1 and 2 make 3. 2 and 1 make 3. 3 and 3 make 6. 3 and 1 make 4. And so on. So it makes it very easy to predict the next coefficients without actually having to do all of that algebraic multiplication that you learned back when you're expanding a binomial. So the next row would be 1, 5, 10, 10, 5, 1. Very easy to just see that. That's pattern recognition. Now, if we saw the whole triangle, it's easy for us to get the 1, 5, 10, 10, 5, 1. But what if we can't see the triangle? How do we then know what that 5th layer is? So actually it'd be the 6th layer if you count the 0, or if you're just counting positive integers, 1, 2, 3, 4, the 5th layer here. So it depends on how you count the layers. But if we go with positive integers, 1st, 2nd, 3rd, 4th, the 5th layer here, how would we know what those numbers are without replicating this triangle? Well, there's 2 ways of doing it. One way is using this notation. This notation uses n and r. N is the exponent to which your binomial is being expanded to. So that's these numbers out here. That is the n. That's the first number written in what looks like a column vector here. The bottom number is the r. Now the r is going to correspond to the exponent on the 2nd term. So if you look at the b, this would be b to the 0, b to the 1, b to the 0, b to the 1, b to the 2, b to the 0, 1, 2, 3, so on. So this is actually the exponent from the 2nd term, the b term in our example here, right? So to calculate it from this, you have to use what's called factorials. Now, factorials are on your calculator also. It's the key here with that x to the exclamation point. You see x, and right next to it looks like x times an exclamation point. That is your factorial key. So you can actually do this in factorials on your calculator. But the faster way is to do it with this NCR key. So I'm introducing this to you because you should at least be exposed to factorials. But when it comes to our skill, we're going to do it through this faster method. Okay? So this formula is actually in your formula sheet as well. It's provided for you by Cambridge. This NCR is not provided as your formula on the formula sheet. So if you're going to use this, you need to keep that in mind, but you don't really have to memorize anything. You just plug it in the calculator. This one, you don't have to memorize because it's on your formula sheet, but you then have to learn how to use it. You either have to learn how to do it manually, or you again have to put it into your calculator. So notice down here, to remind you, the R is your exponent from the B term. The R is the exponent from the B term. So whatever n is, it's the number out here, outside the binomial, n factorial divided by r factorial times n minus r factorial. This is one reason why I generally don't follow this, is because we can use a faster method, and so far Cambridge questions don't require you to actually manually do factorials. Not saying they won't in the future, which is partly why I'm giving you at least a brief introduction, but all the questions in, say, the past 5 years of past papers or more, you can use the NCR and it doesn't matter, okay? So here's an example. If your NR happens to be 5/2, it's not a fraction, it's a kind of like a column vector, this Pascal's notation, then you have 5 factorial over 2 factorial, and then 5 minus 2 is 3, so you get 2 factorial times 3 factorial, because of the n minus r, so 5 minus 2 is 3. What a factorial is you start with the number in front of that exclamation point, and you keep multiplying it by the next number below it, going by integers, all the way until you get to 1. So you get 5 times 4 times 3 times 2 times 1. So 2 factorial would be just 2 times 1, and then 3 factorial would be 3 times 2 times 1, okay? So you write out all of those, and then of course, some of those, because this is multiplication and division and that's opposites, you can cancel some of those. The 2 reduces with the 4, and after you do all the cancellation, all you end up with is the 2 and the 5, and you get 10. If you type it into your calculator just like this, 5 factorial divided by, and you should put parentheses because so your calculator knows that both of those are in the denominator. So if you did 5 factorial divided by parentheses 2 factorial times 3 factorial in parentheses, you will get 10. So this is factorials. This is the key on your calculator. The R, remember, is the exponent from the B term. And this is something you should know as well. Let's say you're doing 5/5, okay? Well, if you do 5/5, you're going to get 5 factorial on top. You're going to get 5 factorial on the bottom. And when you do 5 minus 5, you're going to end up with a 0 factorial. Now, 0 factorial doesn't make sense in the mechanics. That is, to start with the number and keep going down until you get to 1. You can't go down from 0 because 1 is above it, not below it. So this is what is called a defined value. In other words, it doesn't follow the pattern of how all the other numbers work, but it's essential to making the system work, because you can end up with a 0 factorial. But what do we do with it? So when they analyze what happens when you get a 0 factorial, in order to make the system consistent, that value needs to be a 1. So they just define it. 0 factorial equals 1. If you do it on your calculator, it will give you 1. But technically, it's a separate definition that just makes the system consistent. The pattern works for every other number. except for 0. So again, when they analyze where it occurs, the value it needs to be within the working of the math, it needs to have a value of 1, so it's defined that way, okay? So 0 factorial is 1. So all of this here relates to figuring out the coefficients using math. So let's go back to this again. If we're looking at this 5th level, which is why I picked this example, what you need to realize is you don't go by the number of term. In other words, this is the first term, second term, third term, fourth term. Don't think that way. If you think that way, you're going to get confused. What you want to think about with respect to the coefficient is the exponent of b. Don't think about what term you're on. Oh, this is the third term over. That will get you confused. Think about exponent of b. So notice this is b to the 0, b1, b2, b3, b4. So when we're looking at 5, 2, b0 would be this first term, which is obviously going to be a 1. Notice the outer ones. If you have n0 or nn, so like 5, 0 or 5, 5, those are going to both be 1s. Their outside is always 1s. This next kind of diagonal of numbers matches up with the level that you're on. Technically, this one does not fit our positive integer, but we just use it at the top here. So here's level 1, level 2, level 3, level 4. So obviously, the term out here for our 5th level is going to be 1. And the second coefficient, 1 plus 4, is going to be 5. So notice that the next one, so here's b to the 0, b to the 1, b to the 2. Here's our 5th level. When the b exponent is 2, is 10. 4 plus 6 is 10. Notice 5 over 3 would also be 10. You can try that in your calculator. Try doing factorials. Notice you would get 5 factorial. If this is a 3, you would still have 3 factorial for the r, and then 5 minus 3 is 2. So your 2 and 3 would just switch places, but it would be the same factorial. You would still get 10, which is 6 plus 4 right here. And then 5 over 4 would be 5, and then 5 over 5 would be 1 again. So this is notation using factorials. It's just to introduce it to you. You should recognize what factorials are and be able to work with them if you have to. But like I said, the Cambridge questions, you can get by that by using this NCR key. Now, actually, if you take the Statistics 1 book, in Statistics 1, there's a chapter on permutations and combinations. And in that chapter, you will learn about combinations and the NCR key. So we're borrowing this actually from the statistics book, but it is a little bit faster. So if you want to do this 5-2 from the Pascal's notation, instead of doing factorials, you can use this combinations key on your calculator like I showed you earlier, and you would do 5, and then you have to push the NCR, which is actually shift NCR. Okay, so you'd hit 5, shift NCR, and on your calculator, it will just show you a C. So notice I hit 5. Then when I hit shift NCR, you just see the capital C, and then you hit the 2. So it looks like 5C2. And when you hit equals, it just changes it right to 10. So you don't actually have to do manual work. The calculator will do it for you. You still get the 10. So that's why on Cambridge test, time is very important. I use my rule of thumb is the 5 to 7 principle. For every 5 points that a Cambridge question is worth, you have 7 minutes roughly to work it out. So my 5-to-7 ratio, 5 points of Cambridge question points is equivalent to approximately 7 minutes that you have to figure it out. Time is very important. It's a lot more pressure than IGCSE time. So it's important that you can take advantage of these faster ways or more efficient ways of calculating, okay? Now, getting back to this, how does this fit here? Each of these numbers could be replaced with this notation or this notation. So for example, this 1 up here could be written as 0 over 0. Here's the 0 from the n, and the b is also an understood 0 exponent. It could also be written as 0C0 using the NCR key, okay? So this one here would be, first of all, 1 is the n, 0 would be your first b exponent, and this would be 1, 1, so b0, b1. Remember, these are the b exponents. So in NCR, this would be 1C0 and 1C1. This one, let's look at the 2. The 2 would be a 2, this is 0, so this would be a 2, 1. And as an NCR, it would be 2C1, like that. I don't know if that shows up well on the screen, but you can go through and replace all of these numbers either with the Pascal's notation or with the NCR. Again, most important thing to remember, n is the number out here. The r is the exponent of your b. Remember, this is a b0. I did put it up here in the formula, b0, b1, b2, all the way to bn. In here, because it reduced out, I did not put the zeros or the ones. I just put the reduced part. So this would be b0, b1, b2, b3, b4. So make sure that you're paying attention to the exponent of your b term, okay? Now, so that's to explain the coefficients. You need to be able to calculate the coefficients. Like I said, this one right here is going to be the one that I'm going to use in the examples, and it's what I put into your formula. The formula sheet used this, but I don't use factorials. I use the combinations technique, okay? Now let's look for patterns in the variables. And this is going to be extremely important for the skill part in how you get started. If you don't recognize this pattern, you're going to struggle with the skill part, okay? So when we look at the variable pattern, notice the a term starts with the n exponent and goes down by 1. So here's just a to the 0, because that's the 0. This starts with a to the 1. Here's a to the 0, which is why it canceled out. You don't see it. Here's a to the 2, a0. Here's a cubed, a squared, a1, a0. Here's a to the 4, a cubed, a squared, a1, a0. So on the next line, we know it's going to start with a to the 5th, a to the 4th, a to the 3rd, a to the 2, a to the 1, a to the 0, right? The b term goes the opposite. It starts at 0 and goes up by 1. So here's b to the 0, b to the 0, b to the 1. b to the 0 always starts at 0 and goes up. So b0, b1, b2. b0, b1, b2, b3. So again, pay attention to the exponent on your b term. Don't look at, oh, it's the 3rd term in or the 5th term in. Don't think of it that way. Go by your b exponent. b0, b1, b2, b3, b0, b1, b2, b3, b4. The next line, b0, b1, b2, b3, b4, b5. Okay? So that's how the A's and B's go. But remember that A and B are not going to be A and B in the problems. A and B represents a term that has sign, coefficient, variable, exponent. But that A term is going to follow one pattern, and the B term is going to follow the ascending pattern. The A term goes down by one, the B term goes up by one. Now let's look at when they're next to each other. Notice that these A's and B's are actually multiplied together. And if you add up any combination, here's the A's and B's are 0 and 0, they add up to 0. Here the A has a 1, the B has a 0. 1 plus 0 is 1. Here the A is 0, the B is 1, 0 and 1 is 1. Here's 2 plus 0 is 2. 1 plus 1 is 2. 0 plus 2 is 2. Here's 3 plus 0. 0 meaning b to the 0, the exponents. So 3 plus 0, 3. 2 plus 1, 3. 1 plus 2, 3. 3 plus 0, 3. So the combination of the exponents of the A and B add up to n. That's very important for figuring out these Cambridge questions. That's going to be our algebraic part, is adding those. We know that those two exponents of the A and B have to add up to n, whatever n is. Okay, that's extremely important pattern for us. Okay, I think we're done with this. You can always come back and look at it again. Now let me set up with our first example. We're going to move from our mental concept, our pattern recognition, and we're going to try to apply that to the problem solving, the skill part with our first example. Okay, here's our first example, and I've only written part I. I want us to focus on this initial part of the question, then later I'll add the I to it. I kept our formula up here. Anytime you have a formula in your formula sheet, you really need to get used to and comfortable with referring to your formula sheet. You don't want to get to the Cambridge test and not have that understanding of what's on your formula sheet and how you can use it to your advantage. So make sure that when you're on any topic that has your formula in the formula sheet, that you interact with it. That way you know where it's at, and if I've made some changes to it in my teaching, you're familiar with that. Those are very important things for you to get comfortable with throughout this entire A-level series, so that when you get to the test, that formula sheet becomes a benefit to you, and you're not struggling looking where do I find it, and you don't recognize maybe some of the format on it. So I left it up here. Again, remember I'm using the NCR for notation instead of the Pascal's notation. These question types in Cambridge are very distinct, very easy to recognize. As soon as you see the problem, you know it's a binomial expansion problem. They are very skill-oriented, and it's to check to see if you can do it or not. And generally, not always, but they usually prefer a two-step question type, where the first step gives you a basic expansion, and then the second part of the question sees if you can build off of that and see if your mind can do some correlation in it. So the first one is more direct expansion skill, and the second one is more of a mental correlation skill, okay? So in this first one, there are two ways that you can go about it. Really, they're the same method, but one is by algebraically actually figuring it out, and the other way is more of a mental approach. So if you remember when you factored a quadratic equation that had coefficients in the front and the back, and you have to deal with those sets of numbers, and I showed you kind of a way mentally you can figure it out. There is a mental way that you can kind of figure out the numbers. If you're not good at handling numbers mentally, then I would recommend the algebraic way. I'll show you both, and you choose the one that fits, you know, your learning style. Right? So here, what we have here is our binomial, 2 terms. Our n is the 5. Okay, so this binomial is being expanded to the 5th power. Now, in Cambridge questions, they usually do not ask you to expand out the whole expansion. That's not what they're looking for. They're looking for a specific term in the expansion. So we don't want to take a lot of time. You know, if this is 5th power, that means there's 6 terms. We don't want to take time figuring out 6 terms when we only need 1 term. Okay, so that's where your skills training is going to be very important, to efficiently get to that 1 term quickly without doing all the math for it. So this is our n, the 5th term. A is the 2x. Remember, your A and your B represent a term. So the sign is an understood positive. The coefficient is a 2. The variable is x. And the exponent on the variable is 1. Over here, this is B. B is also a term. The sign is a negative. Don't forget the negative goes with the term. So this minus sign goes with that B term. Negative. The coefficient is 1. The variable is x. And if you were to give it an exponent, in the denominator, it's a 1. But if you raise it up, it's actually a negative 1. So if we just look at the x's themselves, this is an x to the 1, and this is an x to the negative 1. That's going to be important for us. Okay? Now, some of your terms may not have an x in it, like if it were just 2, only 2. Then your x would be a 0, x to the 0. Okay? So one thing that's important is the n. Another thing that's important is what are the exponents on your x, your variable, whether it's x or y. Usually they give you x. Okay? Now, out of those 6 terms, remember you have 1 more term than your n. So this is going to expand into 6 terms, but we don't want to do that. We're looking for 1 term, and the term that we're looking for is the term with a coefficient of x, meaning we're looking for an x to the 1 power. Okay, x to the 1 power. This is our coefficient of x. If it happens to say the coefficient independent of x, then that means you're looking for x to the 0 power, because obviously x to the 0 cancels out. And so if it's independent of x, it means it doesn't have an x. That's important. Sometimes students don't understand, what does it mean, independent of x? Okay, so you're looking for a specific term out of those 6 where the exponent on the x is an understood 1, and we're actually looking for the coefficient of the term. Okay, so let's get started here. Again, I'll show you 2 ways. It's really the same method, but one is the algebraic approach and one is a more mental approach. Okay, so the algebraic way, I'll start with that first. Remember when we looked at the pattern of the A, B multiplied together, their exponents added up to n. So the first thing that we're going to do is we're going to put A is going to represent the exponent of A. Okay, so this is our A term. Whatever exponent of our A term is, we don't know, we're just going to call it A. The exponent from our A term, and I'm not talking about this one, I'm talking about the one that comes from here. The exponent from the A plus the exponent from the B, when those get added together, it has to equal n. Now, if you don't follow what I'm saying, go back in the video to when you had this pattern out here. And so you would see like something like ab to the fourth. Notice 1 plus 4 is 5. Or you might have a squared b cubed. Again, adds up to 5. So that's what I'm talking about. The combination of the exponent from the a plus the exponent from the b adds up to n. So a is simply representing the exponent. Exponent of a, exponent of b has to add up to n. That's one equation. So we have two variables, two unknowns, we need two equations. Now, if I'm doing this mentally, again, it's the same method, but if I'm doing it mentally, what I'm going to do is I'm going to list all the possible combinations of integers that give me 5. So I just start off with 5, 0, 4, 1, 3, 2, 2, 3, 1, 4, and 0, 5. So this is my mental approach if I don't want to do it algebraically, right? Now, the second equation has to do with these. Notice this one here, this row here is from the a term, and this row here is from the b term. So remember the a term started at the high exponent and went down by 1. The b term started at the 0 exponent and went up by 1. So this represents the possible a values, and this represents the possible b values, and they have to add together to give me 5. Don't forget that this row is also our r. In the NCR, the exponent of your b term is also your r in our NCR notation, okay? The second part of this, either mentally or algebraically, is a little bit trickier. This one is quite obvious to the pattern that we saw before. Because we're looking for a specific term, Cambridge doesn't usually say, find the third term. Sometimes it will say, write out the first 3 terms, but it doesn't usually say, find the third term. It says, find a term with the coefficient of x, meaning our clue is the exponent in our answer. Needs to be a 1. So when we apply these exponents to our a and to our b, remember this 2x, that's the a term. And this x has a 1 exponent. So whichever one of these numbers, let's just take 4, 1, for example, it means we would have a 4 on this one, and our term over here, the b term, oops, I used red, let me go back to blue. Our b term would be a -1 over x. Again, this x is actually an x to the -1, meaning I could actually write it, if you wanted to, it might make a little more sense, as a -1 x to the -1. You could write it like that. This is the same thing as this. So if this were a 4, this is a 1. So in order to get this result, this is 1 times 4. An exponent raised to an exponent is multiply. So this is going to be x to the 4th. This one is going to be x to the -1. And when you multiply, you add those, you get x to the -3, or sorry, +3. 4 plus a -1 is 3. We're not looking for x cubed. We're looking for x to the 1, okay? So how does this relate to this? This exponent on your x gets multiplied by the exponent on your a term. Remember, this represents the exponent from your a. It's going to get multiplied by 1. So we're going to want to put 1 times a, which is just a. So if this were a squared, we would do 2 times a. 1 times the exponent of a, or 2 times the exponent of a. This one is a negative 1 times the exponent of b. So a negative 1 times their exponent of b is going to be 1, or a minus b. Okay, so it's an understood 1 times our exponent of a, whichever number that happens to be, and a negative 1, that's why it's minus, negative 1 times the exponent of b, whichever that one happens to be. So a negative 1 times the exponent of b, this will equal our outcome that we want. So we want a 1. Okay, so that's how you think through it. You might want to go back and look at this again until you get it in your head. Once you understand what it is you're looking for, it goes faster than this, but initially it takes a little while to understand this one. This one is easy, this one's a little more difficult. So this is how to get this second equation. If I'm doing it mentally, what I want to do is say, okay, 1 times which number here plus negative 1 times which number here gives me 1. So this would be 5 minus 0. Well, that's 5. 4 minus 1, well, we already saw that gives us x cubed. 3 minus 2, oh, that gives us 1. So I just mentally go through it, and this is the combination that we want. A 3, 1 times 3 is 3, plus a negative 1 times 2 is negative 2. 3 plus negative 2, or 3 minus 2, is equal to 1, and that's the outcome that we want. Now, let's see if that works. Well, if I'm going to get rid of these 1s because we don't really need those. If we're solving simultaneous equations, here a and a, so we just subtract, or if you want to add because you have a plus and minus, let's go ahead and add, doesn't matter. You get 2a, the b's cancel, and you get 6. A equals 3, you plug that back in, b equals 2. Same answer. So like I said, you can do it algebraically, it doesn't really take that much time, or you can do it mentally. I usually do it mentally, and you don't even have to necessarily write all of these out. You can, you could even shortcut this a little bit more if you're really good at holding numbers in your head. Okay, so this is a mental way. It's really the same method, but if you like to see what you're doing, do it the algebraic way to be safe. Maybe when you're starting it out, you should probably start with the algebraic way. And once you understand what you're doing, then maybe you can switch over to more of a mental method. Okay, so I know I'm taking some time explaining this. In further examples, I'll go faster, but you really need to understand what you're doing because this question type is pretty much purely a skill, and you have to know what it is that you're doing. Right? So now, how do we get this? The answer is the coefficient, not the exponent. We know how to get the exponent. What is the coefficient? That's where we need to do this. But we're not doing all the terms. We're only doing this specific term. So the NCR, do not use 3, 2 for your NCR. Your N is the 5. This is my N here. This is the R. So what we want is 5, write it up here a little bit higher, 5C2. So be very careful, NCR. The A term is 2x. That is what gets the 3. This is the A. This is the B. The B and the R, same thing. So here you have a negative 1 over x to the second power. This is one term out of this expansion. So this is the coefficient, but your coefficient is going to be further changed by the numbers that are in your A and B. So it's not just the coefficient from the original pattern, it's the coefficient times these other number calculations. So 5C2, we do that really quickly on your calculator. 5 shifts NCR2, and you get 10. So we get 10 times 2 cubed. Don't forget to distribute exponents over multiplication. So you get 8x cubed. Here, a negative squared cancels, positive. If it were cubed, it would still be negative. So be careful with negative signs. Even power, they turn positive. Odd power, they stay negative. So it's positive 1 over x squared. If you prefer to use the x to the negative 1 instead of 1 over x, up to you which way you want to show it. So it becomes that. So 8 times 10 is now 80. X cubed divided by x squared. When you divide, you subtract exponents. 3 minus 2 is 1, which is what we wanted. You don't have to write the 1, it's understood. So your answer is actually the 80. If you write 80x, Cambridge will accept it, but what they're really looking for is the 80. The coefficient is 80, okay? So that is the first part, purely skill in expansion. Now let me write in the second part and I'll show you how it's using this, what you did here, but you need to do some more mental correlation. Okay, here we get to the second part of the question. This first part of the question was only worth 2 points. So you need to be able to do it rather quickly. Like I said, once you understand what you're doing, this will go much faster. Then the second part, this second part is worth 4 points. First, notice the hence. When you see the hence, it means it's directly linked to what you just did. You always want to look at what you did previously when you see hence. We're still after the coefficient of x. It might change it, it might keep it the same. In this case, it still says coefficient of x, okay? And you notice that this part over here is exactly the same as up here. So this term to the 5th power, remember from before, whatever power you have, whatever n is, 1 more is how many terms you have. So if you were to multiply this out, there would be 6 terms here. And if you multiply these 6 terms, the first term, dot, 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 all the way to the 6th term, and then you multiply it by this, you would have to distribute 1 times the first one, 1 times the second, 1 times the third, 1 times the, all the way to the 6th, and then you would go 3x squared times the first times the second times the third, all the way to the 6th. Again, that would be a long process just to find 1 term. So of course, we don't want to do all of that. What we want to do is we want to use something that we've already done to help us find this particular term more quickly, more efficiently, okay? So I'm going to get rid of this because we are not going to expand it all the way out. This is what we need to do, is what's called mental correlation. If I need to end up with an x to the 1, and if my 1 is going to multiply all 6 of those terms, which term specifically do I want it to multiply by to get an x to the 1? Well, I hope that's obvious. To get an x to the 1, I need to multiply 1 by x. 1 times x will give me an x. So I don't need the x to the 0, the constant. I need the x to the 1. I don't need the x squared, the x cubed, the x to whatever. There's only 1 term in that expansion that's going to have an x. And a constant times x gives me x. Mental correlation. Now this term is also going to be multiplied all the way through. So what do I have to multiply an x squared by in order to get x to the 1? Well, that means I need an x to disappear. I need one of the x's on the bottom to cancel. So I need this to multiply by an x to the negative 1 or 1 over x. You can use whichever notation you feel comfortable with. So we need to deduct an x to get to x. Or if you think of division, x squared divided by x cancels to x. Okay? So these are the two particular terms in the expansion that we want. Well, what do you know? We already found the x term. It's right here. So this work has already been done for us. What we don't have is the x to the negative 1. So we need to go back up here, and we need to do the same thing, but I'm going to do it a little faster. And we want to find our coefficient for x to the negative 1. So if we're doing it algebraically, we still need a plus b to equal 5. And we have an a minus b, again, because of our x and x to the 1 and x to the negative 1. But this time we want it to equal a negative 1. So if you're doing it algebraically, you would do it that way. If you're doing it mentally, you would just go through and say, okay, if this was 3 and 2, that gives you x to the 1. If this is 2 and 3, this one, 2 on top, 3 on the bottom, that gives you x to the negative 1. So mentally is a little faster if you know what you're looking for. If you don't quite follow that yet, do it the algebraic way. So we're going to add these together. 2a now equals 4. So a equals 2. When you plug 2 in, b has to equal 3. So we got the 2, 3, same way for that. So we need to go back and do this so that we can find this x to the negative 1 term. So let's do that really quickly. And we're going to get 5. Remember, that's the n. 5c, 3, that's the r. And our a is 2x. This one is to the 2 power. And our negative 1 over x, or if you want to use the x to the negative 1, it doesn't matter. This is our cube. So 5c3, I believe that was also 10. 5c3 is our 10 also. So we get 10 times 2 squared is 4. So that's 4x squared. Don't forget, again, to distribute. And then a negative 1 cubed, that's now negative 1 because it's cubed. So 3 negatives is still negative. Negative 1 over x cubed. And 4 times 10 is 40. Okay, so we get 40. And we have a negative because of our negative 1. And x squared over x cubed is our x to the negative 1, or you could put negative 40 over x, same thing. And that is the term that we need for right here. So now we come back to this. We've identified the two terms that we need. We need the one with the coefficient of x. We have that. We also need the one with the coefficient for our x to the negative 1. We now have that. So now we can put it together and we can say our 1 needs to be multiplied by 80x okay, so our 1 needs to be multiplied by 80x plus, because that's going to be 1 times one of those terms, plus, because we're combining like terms, 3x squared is going to be multiplied by our x to the negative 1 term, which is a negative 40. You can put it over x or x to the negative 1. Again, it doesn't matter which way you write it. So notice 1 times our x term, 80x, plus 3x squared times the x to the negative 1 now gives us a negative 120, and x squared times the x to the negative 1 equals x. These are like terms, so we can add those together. 80 minus 120 is a negative 40x, and we're specifically looking for the coefficient, which is our negative 40. So it's taking a part of what you did in the initial skill, then it's combining with it that mental association, mentally correlating how these patterns connect together. Again, you might have to find an additional term that you didn't find up here, but we did use part of what we did above. That's why this is worth 2 points. This one is worth 4 points. This is a very typical example of a Cambridge question using this question type. So I did this one rather slowly to try to help you understand how to do it. Now let me give us an example, and I'll go a little more quickly through it. Okay, here's our second example. Again, I'm only going to put I up here first until we see what we have to do. Then I'll add the I. Very similar to our last example. Here's our A term, here's our B term. Here's independent of x, meaning we don't want an x, we just want the constant, meaning our exponent is 0. So remember, independent of x implies that your exponent on the x is 0. This time, they're not asking for the coefficient, they give us the coefficient. So I didn't write it here, but this is the coefficient of our independent of x, or in other words, it's the constant. The constant is 540. And so they give us the answer, but they don't give us the coefficient on our B term. So we're kind of working backwards, but really the process is still the same. So don't worry about that K. What we want to focus on is our procedure here. So we're going to do the same thing. We're looking now for a 0, and here's our n. Our n is now a 6. So if we're doing it algebraically, A plus B has to equal 6, because it has to add up to n. Then our exponents here, again, this is x to the 1. This one is an x to the negative 1. So again, we're going to get 1 times our A exponent is A minus B, and we want that to come out to be 0, independent of x, no x. Okay, so we're going to do that for our algebra. If we were doing it mentally, we would do 6, 0, 5, 1, 4, 2, 3, 3, 2, 4, 1, 5, 0, 6. Okay, and if we're looking for the one that gives us 0, 6 on top, 0 on the bottom, 5, since it's divide, you subtract 5 minus 1, 4 minus 2, so the 3 minus 3 would give it to us. That's the mental way. If you solve this the algebraic way, you add 2a equals 6, a equals 3, therefore b also equals 3. So if you're fast at algebra, you can do it like this. And if you rather do it mentally, you do it like that. So now what we want to do is we want to work this out with our formula NCR. So 6C3, so 6 is the N, this is the R over here in the B column. So our A column or B column, the B column is the R column here. So 6C3, and we have 2x to the third and k over x to the third power. So as we solve this, you need your calculator, 6C3, and we get 6C3, you get 20. So we have 20 times 2 cubed is 8x cubed. Here we have a k cubed, so just keep it k cubed over x cubed. And notice when we multiply this out, 20 times 8 is 160. The x cubes cancel, but we still have the k cubed. So 160k cubed, this is a constant. The x's, the variable, canceled out. This constant is what equals our 540. It's the coefficient of our independent of x. So our coefficient, see, 3 minus 3 is x to the 0. So actually the x disappeared. This is the coefficient, equals 540. So when we divide by 160, we actually get, when you do that on your calculator, 540 divided by 160 gives you 27/8. 27/8. If you got a decimal, don't put the decimal down, put the fraction. Use your fraction key to change it to a fraction. Now when you cube root this, cube root, you're going to get k equals 3 halves. K equals 3 halves. That is our first part of our answer here. K equals 3 halves. So let me put the second part on, and we'll keep. So the second part of the question says, for this value of k, meaning the 3 halves, find the coefficient of x squared. So up here, we had x to the 0, but we didn't have k. Now we have k, but we're going to change this to x squared. So we need to do this over again. But now we have this. So if we write this over with our this should be 2x plus. Now this is a 3 halves over x. Pay attention to your main division bar. 3 halves over x means this is the denominator. It's not 2 over x. It's just x, meaning this is x over 1. So when you invert and multiply, it's times 1 over x equals 3 over 2x. So be careful on how you do that. This is your major division bar because it's right here. The 3 halves is the numerator. Do not make this your major division bar. You'd take your 2x, you'd get x over 2, and you'd have 3x over 2. It'd be incorrect. So pay attention to your major division bar there. This is the denominator. This is what gets inverted and multiplied, so you have that. So you have 3 over 2x 6. So this is what we're working with here. And again, we want to do our algebra. So a plus b equals 6, because that's our n. And we still have our a minus b, because we still have an x to the 1 and x to the negative 1. But this time, instead of equaling 0, we want it to equal 2. If we're looking at this, if we have 4 on top and 2 on the bottom, 4 on top and 2 on the bottom, that gives us a 2. If we do it this way, we get 2a equals 8, a equals 4, which means b equals 2. So again, you get 4, 2 either way. And let's go ahead and calculate it out. So we have to do our NCR, 6C. The R is the 2. That's this column here, the 2, 6C2. 2x to the 4th power, and our 3 over 2x to the 2nd power. 6C2 on your calculator, 6C2 is 15. So we get 15 times 2 to the 4th. 2 times 2 is 4, 4 times 4 is 16. So this is 16x to the 4th. This 3 squared is 9 over 4x squared. So if we take 15 times 16 times 9 over 4, we get 540. And x to the fourth over x squared, 4 minus 2 is 2. We got our x squared. It wants the coefficient. The coefficient is 540. This is just a coincidence. That doesn't mean anything. You just happen to get the same number there, but we did end up with 540 again. Just kind of ironic. But 540 is your answer for this. Okay, we'll do one more example and we'll see if you can keep up and understand how this pattern works. Okay, here's our last example. This time it says find the first 3 terms in ascending powers of x. Ascending means going up, okay? First 3 terms, we don't have to do our little algebraic thing this time. We can just go directly into the formula of first, second, and third term. So remember the first one is NCR, so 5C0, because remember the first term, the B has the 0 power, so our R is the power on the B. So 5C0, 5 is the N, times our first term is 1, and that is going to be to the 5th power. I'm going to go ahead and put our negative 2x to the 0 power just so that you can see the pattern here. Here's 0, here's 0. Then plus 5C1. This is the next term. So that means our 1 is now only to the 4th power, and our negative 2x is to the 1st power. Notice the r is the same as the exponent on the b term. That's an important relationship to get into your head. Plus 5C2, 1 cubed, and our negative 2x is now to the 2nd power. So notice 5, 0, 4, 1, 3, 2, all add up to 5. And these numbers have stayed the same here. Now we just calculate this. 5C0, anything with a C0 is a 1, and anything to the 0 power is a 1. So this cancels, and 1 to the 5th is just 1. So all of this is 1 times 1 times 1, 1, plus 5C1, that's 5. So 5 times 1 to the 4th is just 1, negative 2 to the 1, so 5 times negative 2, that's actually a negative 10. And we have x. Then over here we have 5C2. I think we already did 5C2 before. I think it's 10. It is. So this is 10 times 1. And a negative 2 squared is now times 4. That's a 4x squared. So we get a 40x squared. So that's the first 3 terms. Just line it all up, plug it into your calculator, work it out. 1 minus 10x plus 40x squared. First 3 terms, ascending powers of x, x0, x1, x2, and already we have the first part complete. Okay, here's the last part. It says, given that the coefficient of x squared, or that the coefficient of the x squared term of this expansion is 12, find a. So now they give us the answer. The coefficient for the x squared term is 12, although they separate it out. Make sure you pay attention to what that is. So the coefficient x squared term of all of this is 12, so you need to associate 12 with this coefficient. Find the a. Again, these are going to be connected. Notice that this is this up here. So that this trinomial is multiplied by all those terms of this expansion. And like we did before, what does the 1 need multiplied? We don't want to multiply by 1 by all 6 terms. We only want the x squared term. So 1 needs multiplied by an x squared to get an x squared. An x term we don't want to multiply it by all 6. All we want to do is multiply it by the x term. X times x is x squared. We're focusing on just the x squared term. And if you have x squared, how do you multiply an x squared by? You multiply it by the constant. In other words, that's the same thing as x to the 0. So when you multiply by x to the 0, 2 plus 0 is still 2. So this is our mental association, or we're correlating information. So we don't want to multiply it all out. We just want the specific term that it needs multiplied by in order to get this over here. And all of these are already provided. So what we want is we want the 1, that is our constant, 1, or we can start with this one here, 1, this one needs multiplied by the x squared term. That's 40x squared. Plus the ax term needs multiplied by the x term. Well, that's this, a negative 10x. Don't forget to keep the sign with it. Plus the 2x squared gets multiplied by the constant. That's 1. So this comes out to be 40x squared minus 10a x squared. Notice we're ending up with x squareds, plus 2x squared, which equals 42x squared minus 10a x squared. And if we factor out the x squared, this equals 42 minus 10a times x squared. So if this, our coefficient of the x squared is 12. Here's our coefficient of the x squared. So I'm running out of room. 42 minus 10a equals 12. So if we move the 10a over to the other side and we subtract 12, 42 minus 12 is 30. Just enough room here, a equals 3. Okay, so I hope you're able to see that. I hope I wasn't in your way. Here we have, again, 1 needs multiplied by the x squared. There's the x squared from this expansion, which we did up here. The ax needs multiplied by the x. So here's the x term, negative 10x. The 2x squared needs multiplied by the constant. All of these end up being x squared, x squared, x squared, which is what we want. We want the coefficient of x squared. We add it all together, and the coefficient is just the 42 minus 10a. That equals 12. Solve for a equals 3. Hopefully by now you're starting to get a hang of the pattern or different ways that Cambridge can ask this question. And again, good luck. Thank you for joining me in the Zoom room, and I'll see you again next time.